All right, I got the recording started. So like I said, just wanted to do kind of a quick idea of some stuff that we were working on as we move forward from the algebra and into calculus concepts. Now, before we do that though, I do want to focus on graphs and such. Last week we kind of focused on equations. Moving forward though, we definitely need to look at some graphs. So I'll give you a couple minutes to sketch a graph of these two functions for me to make sure that you're comfortable with that, and then we'll move forward into discussing kind of the behavior of these functions. All right, so hopefully you had a chance to try to sketch these graphs yourself. They are things that we should have practice with, from either just collecting ordered pairs, using transformations, or being familiar with the specific details as far as the behavior. The first function I have here, though, I wanted to focus on one that is linear. Okay. As far as graphing is concerned, there is definitely different approaches you can take. One approach that you can start with is building a table. And in this table of values, we'll focus on X and Y. Now, remember, we're in this case, instead of Y, we could put like, hey, whatever the function outputs. But just make sure you remember that Y is the function name. That is our output. We're using the function notation to let us know, though, that, hey, for each input, I'm only going to get one thing back. So no matter what I pick for X, when I plug in a specific number, I should only get one thing back. With that said, I always recommend students start off with stuff like -2, -1, 0, 1, and 2. It really doesn't matter what you plug in. That's just kind of a quick place to start, something a little bit easier to work with. Okay. Now, if you do go through that process and that's what you prefer, it's a little bit more work, but it will get you what you need. Okay. So you would go through there just to give an example of plugging in -2. You'd say, hey, f of -2 equals 2 times -2 minus 3. Instead of X, we plugged in the -2. Working that out is where I got the -7 from. And that would be where I got all my values from. It's just working that out with the negatives. Okay. Now, if you remember, though, a nicer thing about linears is we do have some things that we can use to help us with these graphs. Okay. Anytime you have a linear in the form where you have a coefficient on X and a constant term, and those are your only two terms, you are in the form of y equals mx plus b, where m is our slope and our y-intercept is our b value. Now keep in mind that's going to be 0 comma b when we say y-intercept. We see that with the point that we found earlier right here at 0 comma -3. Now, with that said, though, that means, hey, we can go plot a point at that point, at the ordered pair 0 equals -3. That would be our y-intercept. Now, if you use the table values, we have points that look like this on our graph. If you use the slope, though, we said m was 2. You could write that as 2 over 1, and we could focus on that as a rise over a run. Starting at the value we have here, we say, hey, let's go up 2, and then to the right 1. And then that would give me another point to work with, which you see lines up with what we got when we plugged in +1. Now you can keep repeating that process with the slope up to the right 1, and you'll keep covering up all these points that we've already found by plugging in. Okay. Now, if you're ever in a place where you need to, on like the homework, because sometimes their graphs aren't going to work well with you, know that you can go backwards. Just remember, though, changing the signs. If I change the sign of the numerator, I need to change the sign of the denominator as well. So that would still give us a +2, but that says, hey, I can go down 2, back 1. You won't run into that all the time, but it can happen. Now, the one important thing, though, I do want to point out here, when you start grabbing these ordered pairs and plotting them, it's not about each individual ordered pair. It's about the pattern that they're giving me. Okay. The pattern that these ordered pairs are giving me is definitely the focus of what we're trying to do here. And that's where the function behavior will come into play. So with linears, what we see here is it actually ends up forming a straight line through all these points. All right. And that straight line is what, kind of why we call it linear. We're going to focus on some things about linears in more detail today when we talk about average rate of change. Because if you remember, the reason we call it the slope is because it has a constant rate of change. So that'll be one thing that we look at today. Are there any concerns over graphing this linear function? I know I'm going through stuff like this quickly, kind of like I did last week. So make sure that as you need to review, right, please make sure that you go back to your quiz work that you uploaded, because I went through and graded it as if it was a test. You need to make sure to look at to see how I grade for one, but for two, to make corrections so that we can strengthen the foundation that we need going into this course. Okay. So as mentioned, this first one was linear. The second one we talked about last week is going to be quadratic. Okay, so now we have a quadratic function. With that in place, you definitely could start plugging in points. If you choose to do a table, what you're going to find is -2, -1, 0, 1, and 2. If you plug those numbers in for x, it's not going to quite give you the complete image that you need. Okay. Things that we want to remember is as we deal with a function, we can start to see what we call transformations. So for this particular function, when we say it's quadratic, another way to write that would be like, hey, the parent function, or p of x, just to keep it close to what we're talking about, the parent function of this is just x squared. Okay. If you build a table for something that's just x squared, the parent function works out nice though, because then you could just use the -2, -1, 0, 1, and 2 to work that out. And this is one of the things that we definitely hopefully learn from college algebras, because this gives us a quick way to come over here and say, hey, I can graph these points out and get that done quickly. Just remember here though, this now creates a curve. It's no longer a straight line, it's a curved line in what we call a parabola. Now, what transformation says is, hey, I'm still going to have kind of that same overall shape, but it's not necessarily going to be the same location. And sometimes there could be things like reflections or stretches and shrinks. Okay, but overall, I should expect that same parabola shape that we see here. With that said, though, we do need to highlight some changes. Make sure that you're paying attention to, like, in here, we don't have just x squared, it's x minus 3 squared. On the outside, we have this plus 4. And right in front of the parentheses, we do have a negative here. These are important things to remember. Now, what you're going to find here is another way that we could write this is g of x equals p of x minus 3. Sorry, forgot my name. Negative p of x minus 3 plus 4. Now, the reason I'm rewriting it this way is because we're dealing with stuff as far as compound functions, okay? I'm looking at x squared. We plugged in x minus 3 into x squared. That's where we get x minus 3 squared. But what I want you to see here is, hey, the first thing we have to deal with is what happens with this part that we're starting with on the inside. Order of operations, another great way to kind of explain that. We have to start here. Now, from a transformation perspective, anytime you start on the inside, you're going to see that that's going to focus on what we call horizontal transformations. All right. Now, horizontal transformations, when we look at those, and we talk about transformations, we can compare them kind of back to what we started with. I know that if I take 0 and I square it, I should get 0. Well, what do we have to plug in to get 0? Well, let's take our x minus 3 and see when it's 0. Well, that gives us a quick equation we can solve by adding the 3 to both sides, and we find that, hey, I have to plug in 3 to get 0, right? So if I plug in 3 here, it gives us 3 minus 3, which would then be 0 squared, which is 0. So it's something that, hey, 0 squared is kind of nice to work with. The terminology we use that from transformations, though, is we'll say, hey, there's a horizontal shift. And since it was a positive 3, we would say right 3. Now, the good news is you don't have to do all that work every time. Just make sure you look here and say, hey, I got the 3 here, but because it's negative, I'm going to do the right 3. So for horizontal shifts, we do the opposite. Make sure you see that, hey, it was a negative 3, but we end up shifting right 3. The nice thing about that is we have this origin point here, 0, 0. I can go straight from that origin point and know that, hey, I need to go 1, 2, 3 to the right. So now what we call this axis of symmetry that ran right through the middle of the graph is now going to be over here at x equals 3. Okay, so keep that. We're shifting the whole graph over. Now, as we have horizontal transformations, know that we do have vertical ones as well. That's where we're going to see the other pieces come in because they're outside the part that's being squared. What you're going to find there is the +4 will treat similarly because it's being added to the function. But what you're going to find with the vertical shifts, all we need to do is do as it says. All right, we don't have to worry doing opposite. So with that +4, it's going to take my graph and now move it up 4. So we went right 3. Now we can go up 1, 2, 3, 4. And we actually will have the origin point moved over 3 to the right and up 4. Now we have to be careful though, because as mentioned, we do have that negative in front. And since this is just a -1, what you essentially see here is -1 times the parenthesis here. That's going to be what we call the reflection. It's going to take all the ordered pairs that we were working with and it's going to change the sign. So since all those were positive, all of them become negative, but those are on the y values. So we'd say, hey, there's a vertical reflection. So from here, I'm going to start drawing my graph by saying, hey, instead of doing this upward motion that we did before, I'm going to go downwards. Okay, so let me get this stuff out the way. So we're going to take the same points that we see, but we're just going to plot them going down from what we're going to call the vertex. So make sure you see here, this is going to be a special point that we call the vertex. Okay. I'm going to graph the same shape though, but remember though, it's going down instead of up. Now, some big differences here that we want to make sure to point out when we compare this back towards the linear. This no longer has a constant rate of change. If we take a perspective of function behavior, when I'm going from this point here up to this point, I have to go right and up. Okay, both of those are positive, so that's where we're going to see an increase taking place. So the rate of change over here is going to be positive, and we're actually going to be able to show that it's not always the same, but it's always going to be a positive number. Okay. On the right side of our graph, I would have to go right and down to get from one point to the next. Well, that's positive, that's negative, so we're going to see a negative rate of change or a decrease take place. Okay, we want to make sure to remember these things because that's going to be a lot of the things that we talk about as we move into our first sections of the calculus of these functions. Okay. Any questions or concerns I clear for graphing this quadratic?
So the graph go downward because of the minus?
Yes, of the reflection.
All right, gotcha.
Now, there are times where that negative could be inside. Okay, so keep that in mind. You can have a horizontal reflection too, but those will be situations that, hey, when we come across them, I'll make sure to walk through what to kind of watch for. The nice thing about quadratics, as you see here, there's a clear distinction between going up and going down. That's why I chose to do it with this. As far as the compound functions, I'll make sure to go over that in more detail when we need to as well, because that will come up. Anything else? All right, so I have another function here we can look at. All right. What we're seeing here now is this one's going to be considered a rational function because of the fact that it has a fraction, but more importantly, not just any fraction, it has a variable in the denominator. That x is in the denominator, so we're going to call this rational. Okay. One important thing that you have to remember with your functions is watching for domain restrictions that can take place. So linears and quadratics were nice because the domain is all real numbers. I can multiply and add, subtract with any real number, okay? We see here, even with the exponent of 2, right? I still can multiply, subtract, and raise something to the second power for any real number. However, we do have a problem when we bring a fraction in because now we're introducing division. We have to remember the one thing that we cannot divide by is 0. So anytime you have something with a variable in the denominator, you have to remember that that denominator cannot be 0. Okay. What that means for us here is we have to make sure to check from the beginning what's going on with some restrictions. There's going to be other functions that this comes up with. So you always want to pay attention. What type of function am I working with? Does it have any restricted values or situations that I need to watch for? In this case, as I mentioned, we're highlighting the fact that that x is in the denominator. So we want to make sure to say what would make this denominator 0, because I do not want to use it. So the way that we want to work that out is just take our denominator and say, hey, when is the denominator 0? Now I like to put the slash or the equal sign because we're reminding ourselves, do not use this. Adding the 3 to both sides, we find that, hey, I cannot use 3, right? If we wrote this out, we could write that like, hey, our domain for this is all real numbers, just don't use 3. Okay, we can use any number less than 3, and we can use any number greater than 3, just don't use 3 itself. Now, the reason we focused on that again is because there's a variable in the denominator and we cannot divide by 0. Now, what you're going to find here, though, one important thing when working with rationals is always try to simplify to make it easier for you to work with. Okay, we do want to make it easier to work with. So what we're going to find here is if I take h of x and I factor the numerator because it is a difference of squares, something happens to make this a little bit easier to work with. I get a common factor in the numerator and in the denominator. Okay, I know we kind of talked about this a little bit, so we can then say, hey, h of x can be simplified to x plus 3. Now, the part you have to be careful of, since that's now linear, is make sure not to forget where you started. So what we could do here is just attach to the end that, hey, don't forget, x cannot be 3. I can use this x plus 3 situation, which is really nice, but just don't plug in for 3. So I'm going to go over here and just kind of put a quick reminder for myself. Don't use x equal to 3. I cannot use that. Then I can go plot the points for the linear that we have simplified to. Now I'm going to use the slope-intercept form. So remember here, our m value, our slope is 1, and our b value is 3. So our y-intercept will be 0, 3. And then I can go up 1 and over 1 to draw my line. Now, the part you have to be careful of, though, is that domain restriction. And the way that we handle that is we're going to go in there and say, hey, my line does indeed cross over x equal to 3. So let's zoom in and get rid of that single point. So I'm going to go over here and I'm going to erase that 1 point. And we're just going to put an open circle here. All right, that open circle is what we're going to call a hole in the graph. Now, what I want you to see here, though, what we just did was graph this function. But the nice thing was it could be simplified down to this situation here. Okay, the reason we needed the hole, though, is for that restriction. That would make this denominator 0. So that's why it's very important that we go here. Okay. With it simplifying, though, it did make the graphing part a little bit nice, right? We're able to just go graph a line. But that hole is very important. Things I want you to notice about the hole. If we look at the line, this line goes all the way up until that point on either side. Okay. So if we build a quick little table here of our x values and then what I said, h of x or y values, I could plug in 2, I could plug in 2.5, I can even plug in 2.9. As long as I don't plug in 3, I'm good to go. Right? On the other side of this, we could do the same thing. We could take this same table and say, hey, looking at this hole, I can take my x values. I could plug in 4, I could plug in 3.5, and I could plug in 3.1. Again, as long as I don't plug in 3, I'm good to go. Okay, so please understand that when we draw a hole there, we're going all the way up to that value, but we're not using that value. Okay. Any questions or concerns with where I'm coming from for that graph? All right, so one thing we do have to jump into then is how do we mathematically discuss what's happening here? Because this one had a hole, but what if we couldn't simplify, right? The graphs can definitely get more complex. So we do need a mathematical way to say this. If I can't plug in a number, how do I describe the behavior then that we got going on here? Hopefully what you see, I kind of started that process by saying, hey, let's plug in some stuff around it. Okay. Mathematically, this will bring us into this idea of what we talk about as limits. Limits are used mathematically to look at a particular point on a graph or within a function and discuss what's going on at that particular point by using information around it. Okay. So basically, what you're going to do is you're going to go to every point around something and ask what's going on, but never really talk to that particular point. And then we use all the information we gain to make a conclusion about that point. Well, for example, here we can look at this and say, hey, I definitely can plug in 3 into this situation, right? I could plug a 3 in here because 3 plus 3 is 6. The reason we said we couldn't was because of where we started up here. Okay. Well, let's use our tables here that we looked at. So remember, our focus is here right now. This is where x equals 3. Okay. Our tables here, if we start plugging stuff in, should approach 6. Because as we just said, we can definitely do 3 plus 3. With that said, then, as we look through this process here, if we plug in a 2, we get 5. If you plug in 2.5, you get 5.5. And if you plug in 2.9, you get 5.9. And keep in mind, what I'm using here is h of x equal to that x plus 3, where x cannot be 3. Okay. On the other side, we can do the same thing, but this is going to give us 7, 6.5, and 6.1. Which, nice thing here is we could start seeing some consistent agreement with what's going on. These values are definitely approaching 6 and getting closer. But mathematically, sometimes we want to get more accurate. Okay, so what you're going to find is we want to take these tables and let's add a little bit more information. Let's check at 2.99, excuse me, y'all, and then 2.999. What we're doing here is let's just increase our accuracy to make sure that we get the complete picture that's going on. So I'm continuing my table here. And we'll do the same thing with the other side. Whenever we're greater than 3, we're going to say 3.01 and 3.001. We're trying to get as close as we can to 3. We could definitely get closer than that, but I just want to make sure to show you I'm trying to get as close as I can to 3 without actually plugging in 3 itself. Well, following the pattern that we saw before, we get 5.99, 5.999. Down here it's going to be 6.01 and 6.001. Hopefully you've seen that. That's definitely getting closer to 6. Now, it's still not 6 itself, but it's definitely getting closer to 6. All right. This is where the limit's going to help us, though. All right. The limit is definitely going to help us here because it's going to give us language that shows that, hey, even though I can't plug in x equals 3, it's still pointing to 6. The first thing I want to show you is the work that I just did here, right? I focused on all the values that were less than 3. And then I focused on all the values greater than 3, right? So I used the information around. I looked at values coming from the left-hand side and I looked at values coming from the right-hand side. A great way to write this then, using that idea, is using our limit notation where we'll say, hey, let's try to find the limit as x approaches 3 from the left. Okay, so when I put LIM, we're discussing a limit. And remember, as I mentioned here, a limit, we're just saying, hey, let's try to figure out what's going on a point by using information around it. This little negative sign, kind of written like a exponent there as a superscript, is saying that, hey, I don't want to just look at any point around this value. I only want to look at the points that are less than 3 coming from that left-hand side. Now, the thing we're focused on, though, remember, is our function. So that's where the h of x would come in. It's the limit of whatever's going on here. And again, we can't plug in 3. So that's why the limit is very important right now. Okay. Now, the other way to write this then for the other side would be then to say 3 with a plus sign instead of then the minus sign. Now, again, it's in that superscript like an exponent would be, but we're saying, hey, as this focused on every number less than 3 getting closer to 3 itself, this focuses on every number greater than 3, but still getting closer to 3. That's where this becomes important. What we're saying is let's approach that value without actually using that value itself. Now, based on our tables here, what we see is that both of them approach 6. Okay, which is nice because, as I mentioned before, if we didn't have this piece here and I just gave you this function, right, we didn't have to simplify it. 3 plus 3 is 6. So we definitely see some good agreement that we should have expected. Okay. Now, with that said, then we can take all this into consideration by saying, hey, what's the limit as x approaches 3 of a function? In this case, our h of x. At this point, I do not have that superscript of either a minus sign or a plus sign. Okay, so what you're saying here is, hey, take into consideration both sides, every point from left or right as it approaches 3. What we're going to find is here we had agreement. As we came from the left-hand side, it approached 6. As we came from the right-hand side, again, it approached 6. So we have agreement, but that may not always be the case. We always have to dig into it and look into what's going on. Hopefully you caught on. One great way to do that is plug in some numbers, right? Tables will definitely be a great way to handle that. Is there any questions as far as this introduction to limits? Now, the one thing we have to be careful of is when I talk about limits, this is kind of, it's not necessarily something we're going to use all the time through the course, but it's definitely an important concept that we need to make sure to watch for, that as we discuss what's going on with something, we're using information around a particular point to help describe what that point is doing. Okay. So here's another graph that's fun to work with. Now, as you see at the top here, if you remember, this is what we call a piecewise function because it has 2 pieces with their own behavior, right? The inequality tells you, hey, let's use everything to the left of -2 and then everything to the right of -2. Now, one thing that I did not catch that's wrong here, this should have the equal sign on it. So make sure you fix that. I'm sorry, I did not see that when I copied it over. That bottom one should be greater than or equal to. Now, what you see here, though, is I want us to find the limit of this function g of x, which is graphed here below for you. Okay. Things to look at. What variable are we focused on? Okay. So the nice thing here is we're focusing on x, and that's going to be, for the most part, what we do focus on is our input variable. Our function is in terms of x, so we have a good agreement there. The next thing then is to look at what's the value of x that we're focused on. Okay. So as you see here, they want us to focus on x being 4, and we want to find what's going on as we approach 4 on that x value. So our focus now is down here on this point. We're saying we want to look at this from two different perspectives, and then we want to get the complete picture together. Okay. Well, let's start with the top. This tells me what's going on as we approach 4 from the left side. So we're going to talk about these points over here to the left of 4. Okay. Remember, to the left means values less than that. Well, if we look at this, the nice thing about this is a linear a line, right? Giving us a linear behavior that's decreasing. So we can say, hey, this approaches 4, or as the x values approach 4, my line approaches -1. So we're going to go through all our x values, try to get closer to 4. And as we look at our line, that value for the output approaches -1. Now, the way we're looking at that is this order pair happens to be 4, -1. Okay. But the way the limit approaches it now, remember, we're not just plugging in 4. We're saying, hey, what's going on with all these ordered pairs here? Okay. So as we look at all these ordered pairs, we can see nice agreement that, hey, the pattern that we're following is pointing at -1. So since it's pointing at -1, we would say the limit of g of x as it approaches 4 from the left-hand side, keep that in mind, that's our focus here, is that left-hand side, it approaches -1. So we're not actually plugging in 4, but all the values to the left-hand side are pointing at that ordered pair still, saying, hey, -1 is what I should use. Well, we could do the same thing then for the right side. Okay, we see a similar behavior, right? The line that happens to be decreasing. As we look at all these ordered pairs down here, these ordered pairs happen to point to the same place. Okay. Now, what you're seeing the difference is, like, if we start at 7, we're going from 7 down to 4. Sorry, not 7, 6 down to 4. The y values are going up to that -1. Okay. So it just happens to be that, hey, look at that. It points at -1 again. Once we have the picture from both the left-hand side and right-hand side, we can then discuss what happens at 4. The nice thing about that is, hey, these are both pointing to the same place. So that means the limit as x approaches 4 is going to be -1. Questions or concerns? Now, hopefully you see here then, that's not really the point that we were probably interested in. Okay, as we move forward with this, we're going to have some other conversations, so we're not just going to have time to get into all the details today. Well, what happens with that -2? All right, 4 was nice because that was part of a solid line, right? When we talk about this more, we'll talk about continuity. What we're really interested in is when we see breaks in the line or the line behaving in different ways. That's definitely things that we want to focus on. So if we look at x equals -2, that brings up a question of, like, how do we discuss that? Okay, well, the limit definitely helps us here. The limit is definitely something we want to use to discuss this. So let's go through that process. This first one, we want to look at -2 as we approach from the left-hand side. So we're saying, hey, starting below -2, let's work our way up to that -2 and see what y value the line's pointing to. Well, that's still linear, so that gives us a nice clear path to follow. So if we follow all the points along this line, what we're going to see is, hey, look, it points to the y value of 4. Okay. Now, this is not a point on our graph, so we can't plug in -2 to get to that point. So that's why the limit here is very important. It goes back to what I showed you on our graph here. There's a hole. So we definitely needed the limit to discuss what's going on. With that said, though, since that's still approaching the 4 here, the limit will equal 4. Right? Now, using that same approach from the right-hand side, we're using all the points here, working our way back towards the -2, right? That points to the value of 2, right? So as we do all this, it points to that point right there, which in this case, hey, we could actually plug in a value and get something, but the limit doesn't actually plug that value in. It uses the points around it to say, hey, we're pointing at +2. So we'll get that two there. There's a big difference here though. All right. As I mentioned before, to be able to discuss the limit as x approaches a particular point, we want to look at the left-hand and the right-hand side of that x value. If they agree, as we saw here, they both equal -1, then the limit of that function is going to be -1. What we see here, though, is they're not always going to agree. Now, both of these have meaning in themselves, right? That, hey, as I deal with this, this approach is 4, this one approach is 2, they're good. But the limit as x approaches -2 for the entire function, we would just simply say, hey, this does not exist. And you can just put D and D, okay? There's going to be times where we do all that. We might want this information sometimes, but when we need the overall perspective, hey, it doesn't exist because 2 does not equal 4, okay? Now, keep in mind, as I mentioned, in this case, if you plug in 2, so like if we go say, hey, what is g of -2? We would have to use this second equation here, okay? So if we do that, it'd be -1/2 times -2 plus 1, which will give us sorry. Well, I don't know why I'm multiplying. Sorry. That's 1, not 4, plus 1, which equals 2. Now, keep in mind, this is not the same as the limit. Those are not the same, right? The limit uses the points around something to discuss what's going on. And in this case, the limit doesn't exist at x equals -2 because these do not agree. One side points to one value and the other side points to a different value. Okay. Now, this is still a function that, hey, I can plug in the value for, but because it's a piecewise function, I had to follow what the inequalities told me to do. And like I said, I had to go add the equal sign. That's where the equal sign should have been. And that gave me a point. Okay. These are different things, though. These are not the same. So we have to be careful to understand the limit is discussing what's going on using the information around something, not actually plugging that value in itself. Okay. Any questions or concerns, though, with this graph and this limit that I did here? All right, so I did want to try to start the stuff, but we're sitting at 10:47 now. The next class, we will definitely jump into the average rate of change. And the reason that's important is we're going to be able to start moving towards what we need for calculus. Okay. I wanted to introduce what a limit is today. And as they come up, I'll make sure to review and kind of talk about how they help us. But know that this is going to be important as we move into the average rate of change. Okay. As we kind of talked about our line here before, when I did this first one, a slope was nice to use, but we kind of take things for granted there when we talk about it being a constant rate of change. We're going to have a better way to discuss that moving forward. And that's where the calculus is coming in. And the limit is crucial to setting the foundation for what we need moving forward. So Friday's class, we're going to jump into the average rate of change, and we're going to bring that with the limit to make a good, clear picture for how we can move forward into calculus. If you don't have any further questions, though, have a great day, and we'll see what happens on Friday. Keep a notice out because we may have class in person Friday, we may not. So keep an eye out for all notifications, okay? But have a great day, and I will see you at some point.